the
No,
case.
no, interesting. I'll be happy to take feedback if I made mistakes. So, not that I'm going to mention a lot about it because I
uh,
know very little about statistical physics, but yeah, whatever little I do. So, it's more of the statistics of it and things like that. So, yeah.
okay.
Is this
So,
your entire
uh,
uh,
no, 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 they're not here yet.
right,
There was a
okay.
slight technical glitch, so
Oh,
they're
yeah, yeah.
joining.
No, no, no
Um,
worries. I'm early probably anyway.
so for the session itself, there'll be people from kids from TY and from MSc Part 1 and Part 2 as
Yeah,
well. So,
yeah, okay, that's great. Yeah.
yeah.
So, hello, Vision. It's good to see you. Good evening. So, yeah. No, I was just telling Emma or Emma
Emma.
Jane? Just Emma.
Emma.
Yeah. Okay. So no, I was just telling her. I said if you see any mistakes with statistical physics, feel free to correct me because yeah, you definitely would know more about statistical physics. Yeah, the stats part I get. The economics part, yeah, I get. Physics, yeah, you can correct me. You can add to it. Do whatever you want.
think we should begin. The others can join in as they can. So, good evening, everyone. On behalf of the Society of Physics, I, Emma Jane Chokar, the chairperson, would like to welcome all of you for this talk today. Welcoming Dr. Aditi, our HOD Jyoti ma'am, Bodhne ma'am, Veda ma'am, Leena ma'am, all our faculty from the Department of Physics, and everyone present here. I would really like to thank all our students here who have been able to make it 4 days before their exams. So thank you for being here, and we really look forward to having a great session today. So without any more delay, I would like Rutik to introduce the speaker for the day. Rutik?
Yeah. Today we have with us Dr. Aditi for this informative session on Econophysics. She completed her bachelor's degree in mathematics from St. Xavier's College, Mumbai. She did her MSc and PhD in economics from Indira Gandhi Institute of Development Research, Mumbai. She has also worked as a research assistant with the Bill and Melinda Gates Foundation. She has the experience of working as an economic research officer from 2015 until currently, she has been in Institute of Technology, Bombay. She has also co-authored the book Saving and Investment Propensity of Farm Households: Evidences from India. It is amazing to have you here, ma'am, today and listen to you talk about econophysics. I'm sure everyone here is very excited to learn more about the subject. We welcome you, ma'am.
First of all, before I start, I thank both ma'am for first reaching out and inviting me for this talk, and the Department of Physics and the Society of Physics for all the assistance that they've provided in setting this up. I'm going to quickly just share my presentation so that I can start the talk then. Sorry. Right. Is it visible, Emma?
Yes, ma'am, it is.
Okay, so what I would like to start with today in terms of an overview and right at the outset say is that econophysics is a very broad field in terms of, yes, it is an in-depth analysis in terms of financial markets and everything, but as the name itself suggests, it's the applications of physics and the concepts of physics in economics. Now, which field of economics, which concepts of physics is something which I would like to discuss today. So I'm going to start with a brief overview of an outline of what I'll be covering, which is essentially an introduction. In the introduction, I'm going to talk about and the concepts of physics, economics, the subjects are. But when I say what they are, I'm not going to sort of try and tell you or define what they are. It is more to do with what are the physical laws, what are the economic laws which exist, and why are they related? What are they trying to tell us? What do they try and encapsulate? Right? The reason why those laws are going to be important and why those concepts are necessary is something which I will deal with in that introductory section. And then also discuss maths and statistics in terms of where they fit into the entire larger picture. After which I will come to econophysics in terms of introducing what the subject is with a brief chronology of the developments, just the major ones, because there are quite a few. And as you will see, the developments have happened over time, how all the 3 or 4 fields that you see on top, so physics, economics, maths, and statistics, how these fields evolved, that has what developments in future, right? So then we'll talk about a few aspects, the important aspects of statistics and finance. And what you will realize is, in terms of the slide I intend to cover, is a lot of the concepts of statistics and some of you may have also come across in statistical physics are the aspects which will get applied to understanding some of these concepts. So once we're done with that foundation in terms of what are the most important aspects within the fields of statistics and finance, which would then what you call help us understand what econophysics deals with, That's when I will move on to the important developments which have taken place, and these are the most important developments for field per se, and some of the pioneers of this field itself. Beyond which, I will then restrict myself to just the two different approaches in terms of two different broad classifications of econophysics. So within that, what are the substreams of research? And then, so that's the statistical econophysics and agent-based modeling that you have. And what I'm going to conclude with is a word of caution. Now, the reason why we'll come to that in terms of a word of caution is just like you basically, take some things with a pinch of salt. So basically, trying because it's a merging or coming together of these various fields, you need to understand how each of these fields function. That's why I start with the whole aspect of explaining what these fields entail, what physics entails, what economics entails, and how they come together. So let's start with that. So I'd like to start with a quote by the physicist Macaulay, and he's actually written a book on econophysics, which is titled Dynamics of Markets, Econophysics, and Finance. And I'd urge those of you who are interested in this field to actually read it, where he very simply describes that the world is complicated and physics has made it appear relatively simple. So it's a very nice quote which actually tells you that what is physics in terms of what do we do in physics. You essentially are trying to explain things which are happening around you using these laws in terms of if you're talking about your Newtonian mechanics and all the different, or statistical physics for that matter. So depending on whether you're looking at it from the micro perspective in terms of your atomic lens, or are you looking at it from a macro perspective macroscopic perspective in terms of, and that extends all the way to not just what surrounds us in the world, but across universes for that matter. What happens light years away is also going to be studied as a concept in physics. So physical laws essentially are helping us explain the pattern and the rhythm that we see in the phenomena of nature around us, right? So we try and study those phenomena which are occurring around us. So how do you have the laws of motion? What does it mean to say that you have the force of gravitation? Or what does it mean to say that you essentially the law of inertia, right? So in terms of that, whatever you observe around you is what these physical laws are trying to explain. So then how do these physical laws actually come into place? It's not like someone just comes and gives them to us saying that these are the laws, right? So how do these laws develop? How do they evolve? How they evolve is that there are experiments. You start with a thought experiment saying that, okay, I want to be able to explain certain phenomena. Can I explain it using a set of experiments which help me arrive at that conclusion, right? And then how does it become a law? When I start with a thought experiment, it is not a law. I'm starting with a question that I'm asking, which I'm posing. And then if I'm able to prove it, and then obviously prove it not just with respect to one experiment, it has to hold with respect to repeated experiments. And one of the major underlying features of this is the local invariance principle, which needs to hold. So for example, I'd like to discuss this with respect to an example. The force of the law of gravity, essentially. Everyone knows what the law of gravity is. You essentially say that any two objects would be attracted to each other in such a way that the force is essentially direct proportional to the product of the masses and inversely proportional to the distance squared between them, right? Now, and I'll tell you why I picked this particular example when I also come to the economic. But to talk about that law is talking about not just things which happen within, say, the world framework around us, but you actually extend that to the macroscopic level where you can actually apply those same laws, right? Or for example, your G, the value of G, 9.8 meters per second square, right? That despite repeated experiments and despite all the, so invariant of time, it doesn't matter whether I conduct an experiment to determine the value of G at say 10 in the morning or 12 in the night, or where I conduct it, whether it's sitting in your physics lab or sitting in anywhere else, right? At home. So essentially, that is what is unique in terms of the nature of physical laws. And they have this underlying foundation of local principles, invariant to time, invariant to location, and that forms the theoretical basis for these laws, right? So that is one of the major founding principles, so to speak. Now, these are the two examples which I've given. I've already explained the law of gravitation. The other law which I've mentioned here is Boyle's law for the pressure of a given quantity of gas, which varies inversely with its volume and at constant temperature. And the reason why I mentioned this is when many of you, if you go into researching econophysics, what you will find is that the kinetic theory of gases plays a major role with respect to the statistical physics in it, plays a major role in some of the applications. I'm not sure we'll have time to go into that today, but in case we do, then yes, we can take it up at the end. So that's why this has also been introduced. So these are laws that they would not vary irrespective of where you are doing the experiment, where you are in terms of location. Yes, it may depend on the environment. So yes, it depends on the conditions that you would have around you, but it does not change the values or it does not change the way the bodies respond to each other and how that force is then exerted on each other, right? So given that, now what I want to do is now I want to give you the other side in terms of the perspective from the economic laws. So to start with a quote by two Nobel economists, so William Nordhaus is the latest sort of edition. So both of them have a seminal book on economics. It's a textbook. And if you pick it up, I'm sure all of you will be able to understand it. Very well written. In which, so both of them, William Nordhaus won the Nobel in 2018. So, in terms of both of these economists, the way they've defined it, and this is not a unique definition. If you open any standard economics textbook, you will find multiple ways in which economics has been defined. But this is the most standard one that you would come across if you just open any economics textbook, which is essentially that economics is the study of how societies use scarce resources to produce valuable goods and services and distribute them among the different individuals. Now, why scarce resources? That's one thing I would like to stress. Think about it in terms of the air we breathe. How many times have you actually had to think about, oh my God, will I have air to breathe? But that is you sitting in either, say, Mumbai or in any clean place in terms of, and I'll come to if anyone has a doubt about, okay, air is also a scarce resource, then I'll come to that question at the end. But to answer that, it essentially means that what is scarce needs to be distributed in an equitable, optimal manner. What do I mean by that? For example, take the simplest example of, say, coal. It is a scarce commodity because it is not getting replenished at the same rate at which it is being used, right? Any scarce commodity would require the society to make optimal use of that. So economics comes in. So then you would say, okay, but then you're talking only about these physical goods and resources. But no, that also includes money, right? So economics would deal with how would societies deal with, say, transactions? How would they deal with money resources? How would they deal with goods and commodities? How would they deal with what you call individuals? And when I say across different individuals, it is not just one person at a time. Instead of individuals, I could have said two different countries, economies. So if I consider, so the agent that is being talked about, the economic representative agent is important. That agent, if it is an individual that you're considering, then it is what we call the microeconomic concepts. So you want to see that within a microeconomic, say, in a building, or in, so if you're looking at a smaller group of people and you're trying to see the interaction or the behavior between those economic agents, then you're looking essentially at microeconomic concepts, right? However, if you're looking at it from the point of view of economies, right, you're looking at, and this is the sort of simplest definition in terms of saying that if I'm looking at countries, can you think of, now one question which I would like to pose to you, and maybe you can come back to it at the end if you've not followed it, is when can I think of countries at a micro level? Okay. And that's because that's a whole different stream of research in terms of saying that's the micro foundations of macroeconomics, right? So that's a different stream altogether. But that's something for you to think about. So economic laws, one example which I could give you in terms of comparing physical law and economic law is the following. In physics, if I give you a physical say as A plus B is equal to C, it will always be equal to C irrespective of, because yeah. So if you walked into a store and you wanted to buy any wheat, etc. So maybe not exactly rice or wheat. Let's think of another. Okay. For the time being, we'll go ahead with rice and wheat. But yes, if there's any economists there, those are given goods. So yes, this would not hold. In terms of any goods, you walk into a store and you're looking for a commodity, say X. The minute its price increases, my demand for it is going to fall. This is something which you have you may have heard. If you've not heard, then basically that is talking about the demand, the law of demand. That if my price increases, the price of a good, then I would say that my demand is going to fall because now I'm willing to pay less for that same commodity, the same quantity of commodity, right? And at the same time, if the price falls, then I'm likely to demand more of this particular commodity. My willingness to pay is now increasing, right? So that's the law of demand. There are commodities which defy this law, right? Again, like I said, we can come back to it if some of you have questions about this at the end. So yes, you have laws of demand, laws of supply. For example, you walk into, I'll end with one more example in terms of you walk into a bank and you ask for a loan. You end up paying an interest for the money which the bank gives to you. Or if you've deposited money, then the bank ends up paying you an interest rate. Now, you would expect that that interest rate is always supposed to be positive. Traditionally, economics has always evolved by saying that prices cannot be negative, interest rates cannot be negative, right? But you have and has exhibited the fact that have negative interest rates currently. They're actually trying to incentivize you to spend by not keeping the money. So negative interest rate is for the deposits which are in the bank, right? So in that sense, in economics, you have a slightly different perspective. You're looking at the world from a different lens, so to speak, where data, where events are also going to determine how economics as a field is going to evolve. And then the fluctuations with respect to prices, preferences, tastes and preferences, your income levels would also drive these events at the same time. In terms of optimization, and so I've already talked about micro and macroeconomics. Optimization is with respect to, just like you think about when you're talking about entropy maximization, think about utility maximization. For example, if you as a consumer want to consume a basket of goods and services, right? You would do so such that you would be maximizing your utility. And what would it be constrained by? It would be constrained by what your budget is, what your income is, and so on and so forth. So the reason I'm giving you these examples is to draw parallels with respect to some of the physical laws that you may have studied. And then we can come back to it if you have questions, right? So given this, what are some of the common concepts in both physics and economics? Equilibrium, to begin with, is the simplest concept in physics and economics which I could think of, where I could say that if when you have an equilibrium in physics, you're talking about a state of the system which is not going to change in terms of its internal energy or its state of motion unless it is what you call impacted or disturbed by an external force. And it will continue to remain in that state indefinitely, right? Your law of inertia also states that for the law of motion, right? And that is actually to do with your fluctuations in molecules with respect to differences or which may arise in physical conditions, which would change it. Similarly, in economics, you have what is called a market equilibrium. A market equilibrium is one in which whatever demand is there in the market is met by the supply which is being provided by the producers, right? So this is the simplest way that I can define equilibrium, a market equilibrium in economics. So it represents the balance among the different buyers and the sellers, or as Halvarian put it, your prices would adjust till the amount that the people demand is equal to the amount supplied. So price is that variable which you are allowed to then which would adjust In terms of free markets, yes, it would adjust automatically in order to make sure that these two quantities match, right? And how and when would this change? If there is an external force which changes it. Now, what would the force in economics be? Just like in physics, the force in economics which could change or alter this equilibrium would be either changes in the price levels, changes in tastes and preferences. Sort of. So, if the entire economy is shifting away from its tastes and preferences of, say, consuming rice, right, and it's moving towards wheat, then you would see the shift in equilibrium for the rice market as well as the wheat market, right? So that's the simplest example. Or change in income. Suppose everyone gets a raise in income at the end of the year, right? The entire economy sees that all the people are getting a raise. Then you would see a change in preferences, right? And therefore a change in the demand and supply and the equilibrium. So that's so the common aspect in terms of not having it change once it is attained till an external force changes it, forces the change, is something which I wanted to bring about here. And the micro to macro, the relevance of the economic concepts and the physics concepts is that you have microphysical systems in physics and you can aggregate them to the macro physical concepts. Similarly, in economics, some concepts, yes, you can extend gradually from your macroeconomic to the microeconomic to the macroeconomic aspects, but not all. Okay, so that is our caveat there. What I'm going to now do is I'm going to introduce the following. It talks about this what you call example of how the law of gravity, which I've already explained on the earlier slide, gets applied as is in economics. Now, the reason why I'm going to give you these two examples is the following. When you're talking about econophysics, for those of you who may have read some literature, you may have come across constant applications in finance. However, econophysics, just like any other interdisciplinary field, such as astrophysics or you have biophysics, geophysics, etc., is not restricted in terms of saying that I will only apply the physics concepts to finance and therefore call it econophysics. Yes, there have been major sort of studies and empirical studies in that field, but I would like to classify that as saying that any physical laws or applications of physics in economics would then come under this broader umbrella. The fact that it has been sort of it has been sort of categorized into just the one bracket is something which I think has just happened in terms of the field. So, in order to sort of give you multiple examples, just the two, don't worry, not more. I would like to introduce the model of, which is a model in terms of trade economics, international trade. So you have trade between two countries where you have what is called the gravity model. And very simply put, as you can see on the screen, it essentially says that exports from the ith country to the jth country are directly proportional to the mass, quote unquote, which is essentially the gross domestic product of either of the countries. So the product of the gross domestic products of both the countries, and inversely proportional to the distance between those two countries. The only difference from your traditional law of gravity is that your distance is not squared here, right? So that is a direct application. So if you ever want to sort of research this, you will find ample amount of empirical evidence which supports this. There has been an evolution of this gravity model where you then start including, this is the most vanilla version of the model, okay? So this does not include transaction costs between the two countries. It does not include the economic aspect of tariff. What happens when a country is importing or exporting a good on which it is either itself imposing a tax or a tariff, or when it is exporting, then the opposite country, the country which is importing the good, is imposing a tax or tariff. So transaction costs, what does it take to package it, logistics, etc. Those aspects were then, after Tinbergen introduced this model in 1962, they came up as what you call additional evolution of the gravity model. So you have Anderson, you have Wincourt, etc., bringing in those changes, right? So, and the second example in this regard is, before I move to the financial applications, is that of elasticity. So, elasticity in physics is essentially, most of you would have this in terms of the definition, that what's the ability of any deformed physical body to return to its original shape, right, when it is exposed to external forces. Similarly, in elasticity, we talk about the price elasticity of demand. Okay, how elastic is the quantity demanded for a good with respect to a change in its price, right? And then what you have on the screen is essentially the formula for it. So the percentage change in quantity demanded divided by the percentage change in price. And as long as the absolute value is equal to or greater than 1, it's an elastic good, versus less than 1, meaning it's an inelastic good. Right. So, and the last one I will take at the end if we have time, in terms of the principle of entropy versus utility maximization. Right. So, these are some of the aspects which I wanted to sort of introduce before I then moved on completely to the financial applications. Because I know that those of you who have read would then consider only those applications. But no, in my opinion, you would have econophysics as any applications of physics to answer some of the problems that economics faces. Right? So, with respect to that, what is then across both these fields, what is the most common language that would connect them? Right? So, mathematics and statistics are what are used as underlying sort of the language to uncover the laws in both physics as well as in economics. Economics, starting say 1970s, is when maths entered the picture and the models, the mathematic modeling entered the picture. But physics has always had a mathematical foundation in terms of interpreting the laws and in terms of even discovering understand both these as well, economics. And statistics, the reason why I've listed out some of these points over here is because these are some of the basic concepts that one of the aware of before taking it up for further research or study. And statistics is essentially nothing but the science of collection, presentation, analysis of that. You can extend the microscopic laws that you may have seen and try and see whether they are also then satisfied in the macro. So, but based on the microscopic laws, right? So these statistical laws are essentially dealing with or resulting from the presence of the large number of particles which form the body, right? And then and these cannot be reduced to mechanical laws. The reason why that sense is important is this is actually a definition from Landau and Lifshitz, their textbook. So, in terms of the reason why that is important is because that then introduces the whole statistical domain of probability into the picture. Because you cannot reduce these to hard mechanical laws, right? The whole field of statistical mechanics. And that is something which that's exactly why it is useful to explain concepts in economics. Because in economics, most, like I've said, it's not set in stone. Because the minute you find something which does not obey the law, and obviously you have proof for it, you can actually say that the law is therefore not set in stone, right? So because of the probabilistic nature of many of these concepts, it is the statistical mechanics which finds applications in economics, in the financial part of economics. So what is econophysics then? You are essentially talking about empirically based models or data-driven models of which are trying to help us understand the financial market dynamics and what part of financial market dynamics, namely volatility, price dynamics, derivative construction, and then what's the final aim? To be able to model this instability which exists in the financial markets. Why is this a concern? Why is there any instability in the financial markets? And we'll talk about this when we're talking about agent-based modeling, in terms of saying that not all the people that are going to be in the financial market, either as traders or so buyers and sellers essentially, it is behavioral and it is difficult to be able to what you call explain what how the market, or when they say how do you it is difficult to explain how market will react. What does it mean? What it means is that you cannot dictate the behavior of a buyer or a seller. Whether a person, you can say that okay, with such and such a probability, or depending on the trend that I've seen in the past whatever few months or few years or etc., I can take a call and say that okay, given on that I can based on that I can predict what will happen to the market, say 2 days down the line, 1 week down the line, etc. But that is not 100% certainty. Okay, so it is not with 100% certainty that I can make that claim. Right? So this is a definition which you will come across in terms of the writings of Stanley, Eugene Stanley, who is actually the pioneer in terms of the terminology. So in 1995, Eugene Stanley, a physicist, was actually attending a conference in Kolkata, and that's where he coined this term of econophysics. And that's where he then introduced, but that was not the first time that econophysics, with respect to the applications of statistical physics in economics, was introduced. That's not the first time. It goes back all the way to 1900s, where you first had the concepts of, say, a random walk or Brownian motion entering the picture and being used to understand the movements in financial markets. So it is not 1995 that econophysics as a field emerged. Okay. Yes, the developments happened more so after the 90s. There's a reason for that. Till the 90s, you did not have complete computerized financial markets in many countries, right? So till say 70s, 80s, and obviously the advanced countries got computerized early on, but you did not have the type of data, the type of stock market analysis that you now see at the click of a button. You go to the website of Bombay Stock Exchange, and the click of a button, you will have all the days, rates, and the time series for every single. So when I say time series, just the price levels for, say, years together, at least 5 years together, or even Google. In Google, you put in any company's name, and you will essentially have a 5-year graph right in front of you at the click of a button, right? Now, that is something which was not very easily available when systems were not computerized. So yes, econophysics in the financial markets has grown as a field ever since this computerization took place. And that's why you see more and more people writing research papers and doing research in that field now. And like I said, does not mean it did not exist before. And we'll talk about some of the seminal papers here as well. So that was just the precursor to econophysics. So Eugene Stanley is the one who introduces it, but you have Mantegna and Stanley. They've come up with a textbook which also discusses econophysics. In terms of the references, Bijan, if you could take note, if there's anyone who requests a specific reference, I can obviously send you guys a list and let me know if you need that. Right? So the roots of econophysics were essentially set in the paper by an Italian physicist, Majorana, which gave the analogy between the statistical laws of physics and the social sciences. And that's actually from Mantegna and Stanley's book in 2000. So where it's not even discussed with respect to financial markets. So if you go back and look at that study, you will find that it talks about income distributions and wealth distributions, because that was a major sort of, not just a research area, but in terms of trying to see how that is something which is not going to be uniform. Depending on which country you're analyzing, depending on which state in that country, depending on which village in that country, you will have different income distributions, wealth distributions across the board, right? And then the minute you take it one step further and say, okay, across countries, then it's going to be a totally different volume. You have your advanced countries, you have your lesser developed countries, and so on. So that's where Majorana actually comes in with econophysics for the what you call trying to answer the economic problems, right? So this is just a chronology of some of the developments in terms of 30s and 50s. 60s and 70s is when you have Mandelbrot's seminal work in finance in 1960 and 63. You have pharma coming up with the efficient market hypothesis. I'll talk about all these, so don't worry. I'll talk about all the concepts which are given here. In terms of the papers which have been written, the seminal works, these are some of the seminal works that have been conducted. And like I said, in the 60s and 70s and in the 30s to 50s, as you can see, the amount of work which was done was not as the field was still developing. Plus, you did not have, say, access to the financial markets as much as you do today, right? So 1990s onwards is when you have this huge spurt in many people sort of taking this up as for research, for empirical research. So now, based on what you've just seen here, what I want to do is I want to do the following. Like I said in the outline, I want to introduce some of the major concepts which of statistics and of finance, which are, so in statistics you will see the concepts of economics as well, physics as well, which appear, and therefore I call them as important what you call concepts in statistics. But you will see there's random walk, there's Brownian motion, there's geometric Brownian motion, etc., so on and so forth, which appear as the important concepts which you would require to understand the developments in econophysics, right? So I'll discuss those what you call concepts and then move on to the two strands of literature in econophysics with respect to finance. So starting with probability, sorry for the typo there. It discusses Kolmogorov's axiomatic approach, which is nothing but the theory of probability as a mathematical discipline which can be developed from axioms and independent of the what you call meaning of the elements and their relations. So the theory of probability, and this is again something which you will see if you open any standard or text on econometrics or statistics, where you will have multiple approaches to probability. So the axiomatic approach is what gets implemented when we're talking about econophysics, statistical physics, and so on and so forth. Where the way the sample space is defined is essentially the set of all possible outcomes of a random experiment, and that is a sigma field. In terms of, and then the ordered pair, omega s is the sample space. What is a probability measure then? You're essentially then now imposing those axioms with respect to the probability measure, where you say that omega s is your sample space, but you are now defining a real valued function on that particular sample space, which satisfies the three conditions which you have on your screen. And if and only if those are satisfied, would you then have a probability measure? E would be a probability measure. The three conditions are essentially your non-negativity, the probability of the entire sample space is 1, and countable additivity. Please let me know if you have doubts with this and I can come back and explain this. Yeah? So then once you've understood what is probability, what is a sample space, you introduce the concept of a random variable. Now, for some of you who may have studied what a random variable is or know what a random variable is, this would be obvious. But for those of you who don't, you're essentially talking about random variable not from the notion of probability. You are not saying that a random variable is something which has a probability assigned to it. It is essentially a real valued function. It is not necessary that we are talking about probability. When we assign probability, you will talk about it in terms of either a discrete or a continuous random variable. But till you don't talk about what you call the function, the values of the function itself, if they're not probabilities, fine. It is still a random variable because it is still taking those real values which you are assigning to it. Right? So that's essentially the definition. All these definitions are essentially from Natsne's book on econometrics in 2004. Right? And you essentially then define it as such for all the Borel sets. And so if anyone wants those definitions, let me know. I can give you those as well. You're essentially saying that it is true that the inverse image of every Borel set on the real line is an element of S, and then X is said to be a random variable, if and only if X is defined from omega to R. Right? So based on what is a random variable, if I were to then introduce what's a distribution function. A distribution function is essentially, it's also called a cumulative distribution function. It's what's defined on your screen as you have a random variable. It's defined on a probability space. So now the minute I say it's a random variable defined on a probability space, then yes, each of the values that I'm assigning to X are those probabilities which are getting assigned to it, right? And then the distribution function is essentially the probability that x takes a value lesser than or equal to x, and what you have is probability of x inverse going from minus infinity, sorry, there should have been a minus infinity there, minus infinity to x, right? And then f is called the distribution function. Probability density function for a continuous random variable is essentially talking about this distribution of all these probabilities across the interval on which it is then defined. Or, in other words, it is nothing but the derivative of your cumulative distribution function for this particular random variable, right? And the two important properties which are mentioned there, as in the parenthesis, are essentially non-negativity and the fact that the probabilities have to sum to 1 over the interval on which the random variable is defined. Coming to what are theoretical probability distributions. I know some of you may have heard about what is a Gaussian distribution or a normal distribution, but what are theoretical probability distributions? Why do we need to define these distributions? The reason why we need to define these distributions is your probability density function, which is given for a continuous random variable. We want to see whether this random variable is the density function of it, whether it adheres to or it follows any known probability distribution or any theoretical probability distribution. Now, why am I saying that? The reason why I'm saying that is the following. If I can say that the random variable follows a certain distribution, then I can clearly, based on the properties of the known distribution, make claims or make inferences about the random variable at hand. That's the only reason why you have a separate set of theoretical probability distributions, right? So that's why it's important. And why is it important to know what these theoretical probability distributions are? Across the field of econophysics, you will always be starting by saying that, assuming it follows a certain distribution, you either empirically try and prove the hypothesis that it follows the same distribution, or it gets disproved in terms of saying, oh no, I found a different distribution that it is following, right? So that's where the theoretical probability distributions come in. What is an empirical distribution then? Macaulay in 2004 in his book, the one which I've already stated, defines what an empirical distribution is. So this is the mathematical definition which he has. Sorry, does someone have a question? Right. So where he says that you consider n one-dimensional points, you arrange them linearly, and your px is essentially the probability that the point lies to the left of x on your x-axis. So you arrange them along the x-axis, and your empirical probability distribution is nothing but the sum of theta times the difference of x minus xi, so that deviation divided by n. So it's an average of sorts, where your theta x is only 1 when your x is lying between, when your x is greater than or equal to 0, when your x is positive, right? And it's 0 otherwise. And xk is essentially nothing but the, or because you have the limits of 1 to k, it's where k is the nearest point to the left of x, right? So then what's a Gaussian normal, or Gaussian or a normal distribution? This is something which most of you would be familiar with, where you're talking about a continuous random variable following the bell-shaped, the traditionally called bell-shaped distribution, right? Or your normal distribution. If its probability density function is given by the equation that you see on the screen, where your frequencies are essentially equal to 1 over sigma root 2 pi and e raised to minus half x minus mu by sigma the whole square, then that's a normally distributed random variable. The second, what you call most important theoretical distribution that you would come across, especially in finance, is the log normal distribution. And we'll come to this when I talk about the returns in finance. The log normal distribution is essentially, it derives from the normal distribution, wherein you're talking with if a random variable x is normally distributed, sorry, that should have been with mu sigma square, and the random variable y is the natural log of x, then y is said to follow a log normal distribution, right? What have I not covered in these concepts? What I have not covered is independent random variables, your conditional and marginal probability density function, probability distributions, and convergence and the types of convergence. Okay, so feel free to pick up a standard statistics text or ask me at the end of the talk, right? Based on this, what the next important point, because we've been constantly talking about how you extend the microscopic to the macroscopic, what you call physical systems as well as economic systems, the next point is how do you do that? That's where aggregation comes in, right? So statistics has very neatly defined tools to sort of help you aggregate, right? The smaller elements to the macro elements, and macro elements meaning aggregate all these smaller elements and then say that therefore the macro system also would behave in a certain manner. And the most what you call famous theorem which gets applied is the central limit theorem, which is also based on the weak law of large numbers. So the weak law of large numbers I've put there just as a precursor to the central limit theorem, but the takeaway is the central limit theorem, where you're saying that if xi are essentially independent and identically distributed random variables with mu as your mean of every single random variable that you have, and the variance sigma square, both have to be finite. And this is the Lindbergh-Levy version of the theorem. There are different forms of the central limit theorem as well. So then if you define Zn as essentially the deviations of the sum Sn essentially is the sum of all these elements xi from the mean divided by sigma root n, then your Zn is then supposed to converge in distribution to Z, right? And Z essentially follows a normal distribution. So you can then say that Z converges in distribution to a normally distributed Z, right? So that's the aggregation of it, because you started with xi's which were independent and identically distributed. You didn't say anything with respect to whether it was normally distributed or whether it had any other distribution. All you knew was that each of the elements of this particular sequence of random variables had the same mean and had the same variance. I'm making the assumption that everyone knows what mean and variance is. And then you have convergence and distribution. Like I said, I can take it up if you have a doubt regarding what that means. Following this, what I want to now introduce is what is a stochastic process. And I'm aware you may have studied what stochastic processes are in physics as well. So coming to the mathematical or statistical definition of it, a stochastic process is nothing but a collection of your random variables where each of these random variables is then going to be defined on the probability space, essentially saying that each of these random variables is going to get assigned a probability, right? In the discrete case. In the continuous case, you're not assigning a single probability to it, right? You can only make the claim that the probability distribution may be following a certain theoretical distribution and then make inferences about it. So remember one thing, with the continuous random variable, the probability at a point is 0, right? So if the index set in this particular case is countable, then your x is discrete. It's a discrete stochastic process. If it is uncountable, it's it's a continuous stochastic process. And if I refers to time, then x is a time series. The reason why that's italicized is the following. Across most of economics, what is interesting when you actually try and figure out laws in economics, or when you're trying to study the behavior of an economy or of individuals, what is important is to see how they behave over time. That is not to say that it is not important to see how they behave at a point in time. It is just to say that you can gather much more if you study their behavior over time. The behavior of economies, the behavior of agents, the behavior of individuals, the behavior of financial markets. So when I refers to time, that's when you're talking about X, the stochastic process X, as a time series, right? That's the most important takeaway. The reason being, all financial studies would be dealing with data sets which are across time, price levels across time, returns across time. I'll come to what these terms mean, so don't worry about that. So now coming to some of the concepts, like I said, which you would have come across in physics, are Brownian motion and geometric Brownian motion. Why are these important? These are important because, like I said, in the financial markets, you have established studies, empirical studies, which actually talk about how these financial market dynamics in terms of either stock prices, in terms of what you call the returns follow one of these motion processes. So you either follow a Brownian motion process, and by the way, Brownian motion not for the returns. For returns, you will have geometric Brownian motion because you're talking. Sorry, for prices. For prices, you will have geometric Brownian motion because in geometric Brownian motion, you cannot have negative values. And like I said, we always talk about prices as being greater than or equal to zero, right? Whereas in Brownian motion, you can have negative values. So returns, yes, you can talk of returns following, and I'll define returns in a couple of slides now. So Brownian motion, this is essentially the what you call definition of what Brownian motion is. You can find most of these definitions in Campbell, Lowe, and McKinley, which is the seminal text when it comes to understanding finance as well as statistics, all in one book, right? So Brownian motion essentially is talking about a continuous time process which is related to the discrete time random walk, right? How does it do that? You define this continuous time process based on the discrete time random walk, and so you basically partition the interval and then construct P and T. And PT is the limiting process. So as n tends to infinity, you have PT, which is normally distributed. And if the stochastic process PT follows 1, 2, and 3, then your PT is said to be a Brownian motion or a process or a Wiener process, right? What are those three conditions? That for all the time periods, T1, T2, any two time periods essentially, the difference in those values of that continuous time process should follow a normal distribution with the mean and variance which are derived based on, so which are dependent only on the difference in the time. They're not dependent on either of the values or anything. They are dependent only on the difference in the time. Similarly, that extends to, say, 4 time periods, right? When it extends to 4 time periods, if you take a set of any 2 increments, then those 2 should be statistically independent of each other. They should not be impacting each other, right? And the sample paths have to be continuous. You're not talking about discrete jumps in the data. Jump data is a separate substream of finance. So, and then where does geometric Brownian motion come in? You're essentially, in the simplest of terms, talking about the non-negative version, and where you have a stochastic process which is defined as ST is equal to S0 exponential, so e raised to xt, where, so this essentially, if you were to take the logs, essentially, you would come up with a stochastic differential equation, where xt would be nothing but sigma times bt, where bt is a Brownian motion process, and plus mu t, where your mu is the mean of the mean of xt, and you essentially are then saying that then and only then is st supposed to be a geometric Brownian motion process, right? And s naught is the initial value. Okay. Now, based on that, if I were to now extend and introduce the concepts which are which you will come across fairly regularly in finance, which are the most important or the most empirically researched concepts as well in finance, what do you think of when you think about the term finance? You're thinking about stock markets, you're thinking about stock prices, market increased by such amount, it fell by such a level. What does it mean? What are we trying to do? Who are these investors? Who are the people who are investing? Who are the people who are selling, right? In order to understand that, what you need to understand is the following concept. Financial markets are essentially transactions, or they are powerhouses in terms of facilitating the transactions between the buyers and the sellers, right? Where you have the traders, the traders who would either buy or sell the shares. You would have individuals as well. I'm not talking just about your stock traders or your brokers, etc. You would have any two individuals. Let's simplify it. Any two individuals, they want to sell the simplest asset, a share, right? They want to sell. One person wants to sell, one person wants to buy. Through a financial market, the way it's all computerized, if you want, you can go and read the history of it. It's very different in terms of how transactions used to take place. But currently, click of a button, you have a certain number of shares at the end of the day sitting in your account, right? But provided someone else is willing to sell that particular amount. Okay, so When I say provided that person is willing to sell, if the market does not have supply for the number of shares that you have requested, the trade will not take place. You cannot force someone to sell something to you just because you want it. Okay, the ledger or the book or the what you call record keeping device is then called, where you basically put your buy request and someone else puts their sell request, is what is called a limit order book. We won't have time to go into the details of a limit order book, but with respect to the dealings in markets, what is important is trying to understand risk involved. Risk involved. Why is there risk involved in this? The risk is involved because you don't know whether a company is going to do well and therefore its price is going to increase, stock price, or it's going to perform poorly. For example, the mergers of, say, your Lakshmi Vilas Bank. Yeah. So, is it beneficial to the investors who are investing in the bank which has gone bankrupt, or is it beneficial to the investors of the bank which is taking on this bankrupt company? It is actually beneficial for the ones who've gone bankrupt. But at the same time, why is a safe bank taking it up? Risk involved, right? Stock price. You don't know upfront, sitting today, whether a company is going to do well tomorrow, instantly, right? That's the risk involved. Volatility. TCS goes and announce their results, Tata Consultancy, right? They go and announce their results, their quarterly results, and they've done very well despite COVID. What happens to their share prices? Skyrocket high, which was just very low, say, yesterday, right? Volatility. Or another example, which everyone is aware of, the 2008 financial crash, right? Overnight, within split seconds, you have a huge dip in the market in terms of the indices crashing. What is that pertaining to? Volatility. Now, that is not to say that just that one blip is volatility. That blip over time is what is going to define volatility, right? So, over time, how many blips, how many rises, how many crashes do you have? Those shocks are determining the volatility in the market, right? Now, with respect to financial markets, you will see that the focus is always on the returns. How much am I getting based on how much I have put into the market, how much I have invested, what is the return I'm getting? And the return in simple terms is defined as PT by PT minus 1, where PT is the actual price of the asset. Now, when I say asset, it could be a stock, it could be a derivative, it could be an option, it could be n number of assets, right? But therefore, I've written only price of an asset at time t versus time t minus 1. And your simplest definition of a return is what you have on the screen. And simple gross return, annualized return are also given there. Continuously compounded returns, you know the difference between simple interest and compound interest. Your compounded returns are essentially the logarithmic returns, logarithmic logarithmic simple gross returns, right? And when you expand that, you essentially end up as getting just the difference of the log of price today minus the log of price yesterday. Or, by the way, how do you define t and t minus 1? Is it always today versus yesterday? Not necessarily. Given the fact that I have computerized data, it could very well be t at, say, what's the time now? T at, say, 5:10 versus t minus 1 being 5:09. It could be minute-wise, it could be tick data, second-wise. Bombay Stock Exchange actually boasts nanosecond level data. Okay, so that's how how small your time series or the time tick data refers to when you have microseconds coming into the picture, nanoseconds coming into the picture, right? So an excess return is essentially when you have an assets return with reference to a riskless asset. What's a riskless asset? A riskless asset is actually an ideal sort of an asset. Why do I say ideal? Just like the term suggests, we're talking about an asset which does not have any risk involved. That if I say that I've put in money, I will definitely get a certain return which is promised at the end of the duration for which the investment has been made, right? For example, What is a common example given here is that of a treasury bill or your government bonds in the Indian context, right? Your government bonds. Why are they riskless? They are considered riskless because you assume that the government is never going to default. Can it default? Yes. But will it default? You're saying out of all the assets given to me, it's the one with the least risk. Okay, so that's why riskless. Right? So one of the concepts which is also important in finance, this is actually a statistical definition here, but I've put it with the financial terms for the following reason. I've just introduced returns. One of the empirically established results is that returns exhibit what are called fat tail distributions, where fat tail distributions are referring to if you are given any curve, any theoretical distribution. Predominantly in this particular case, we're talking about normal distribution. Then we're talking about fatter tails. Okay, so you know the bell-shaped curve. Imagine you have what you call a kurtosis, and this is just your basic measures of central tendency. If you're talking about what is the kurtosis or the property of the peakness of a curve, your fat tails are essentially when your kurtosis is going to be higher than 3. Okay, so excess kurtosis is essentially a sample kurtosis minus 3. So high positive values of this particular measure of central tendency is what is referred to as a fat tail or a leptokurtic distribution. And returns have very what you call frequently been termed as having fat tail distribution. Now, what does it mean? It essentially is talking about the capturing the occurrences of essentially your volatile behavior. So when you have extremely high returns versus when you have extremely low returns, which is actually what is causing the kurtosis. Okay, higher the number of occurrences, higher the kurtosis, right? So this is again in terms of, that's why I've put down the studies in terms of those which have found the evidence of fat tail behavior. And how is this captured within the data? You model the continuously compounded return which you saw on the previous slide as in the distribution of it. That has been found to be non-normal, but what you call belongs to what is called a stable class of distributions. So non-normal with fat tail behavior and comes from a stable class of distribution. So then what is a stable class of distribution? Or what is a stable distribution? Stable distribution is nothing but when you're generalizing your natural generalization of your normal distribution, which is stable under addition. So when you take the sum of your stable random variables, then the result is also a stable random variable, right? So normal distribution, because we're dealing with that when we're talking about Gaussian returns or non-Gaussian returns, is a special case of a stable distribution, right? And a drawback of this is that we are essentially saying, why is there a drawback? The drawback is that we're talking about what you call the stock returns having infinite variance, which is not always true. Like I said, in economics, the research shows that just because one person's found some evidence based on the empirical data, it's not necessary that someone else has found the exact same result. Okay? Based on that, in financial markets, Emma, how much time do I have? Because I think it's already 5:10, but it's okay. I'll try and wrap up fast. Yeah? Yes,
Okay,
you were
ma'am.
saying? Sorry, how much time do I have?
So we've already finished, completed 5. So,
Yeah, okay, fine. So I'll try wrapping up faster.
yeah.
With respect to financial markets, one of the most important aspects is that of efficiency. What do you mean by an efficient market? And when I say efficient, it is with respect to informational efficiency. The degree to which market prices correctly and quickly reflect information which has come into the market and which are then incorporated into the value of an underlying asset, right? That is what is called as efficiency. So then what's the efficient market hypothesis? That if you have this informationally efficient market where all the information which is coming in is instantly processed and incorporated into the value of the asset, then you essentially are saying that the price changes are not predictable, right? Why are they not predictable? Because all the information which came in was instantly incorporated. Therefore, I cannot predict, because every second, if there's new information that's coming in, I cannot predict what is going to happen to the price instantly, right? So, therefore, in an informationally efficient market, and how is this then tested? Because this is one of the most researched topics across financial literature that you will find. So, for example, in pharma, pharma in 1970 is the one who actually defined this efficient market, where he says that prices always fully reflect the available information. And Malkiel basically extended that definition to include a few more aspects, where he then introduced weak form, semi-strong form, and strong form of efficiency. Okay. So now, based on all these concepts, I'm going to go through the important developments in econophysics. You have the first paper by Bachelor in 1900, which formulated the theory of Brownian motion as being able to explain the actual stock price fluctuations, not the returns, stock price fluctuations in the Paris Bourse. Okay, so that's the sort of first seminal paper that you have before even 1936, where Majorana actually came up with the wealth distribution paper. So if you wanted the financial market paper, then Bachelor is the first one, right? Mandelbrot and Fama are the ones who then went and found the departure from the log returns from Gaussian behavior, right? Because just in the preceding slide, I'd shown you that there were people who actually established the Gaussian returns, but you have Mandelbrot and Fama in the seminal papers who actually say that no, log returns are actually not normal. So and then you have Osborne in 1959, who's also found the fact-tail distributions, which would lead to the errors with infinite variance, right? So Osborne actually went ahead and found that they were supposed to be Gaussian. But you have Mandelbrot and Fama who come and say that no, we actually find evidence of fact-tails in the distribution, and therefore it is actually a departure from normal behavior, right? But these papers, in terms of Mandelbrot, Fama, you later on had Fama and French also, these laid the foundation for mathematical finance, empirically studying these distributions across the different markets and then proving or disproving whether they were Gaussian or not. This was followed by the developments with respect to Ito calculus, wherein Ito is a Japanese statistician who actually introduced, or he's also known as the father of modern statistical analysis, who basically developed stochastic finance, right? So you have that, and then he brings about geometric motion as one of the major Ito processes. And geometric Brownian motion is actually what forms the foundation for your Black-Scholes option pricing model, for which Scholes and Merton, so Black-Scholes and Merton, for which Black-Scholes and Merton in the same year ended up figuring out the same model for option pricing. And eventually Scholes and Merton won the Nobel for it because Black had already passed away before that happened, right? So that's essentially Black-Scholes. And Black-Scholes actually established Gaussian log returns. So you see, in the same span of a decade, you have seminal papers which are actually depicting opposite behavior, right? This depends on the assumptions which they would have made, what was the data under consideration, what were their theories based on which they were actually studying this, and so on, right? So coming to the two approaches in econophysics, you can find a very nice review in a set of two papers by Chakrabarti et al. In 2011, where they actually give these two categorizations of statistical econophysics and agent-based modeling, where statistical econophysics is nothing but your existing stylized facts of the data, and you're trying to study the microstructure of the markets, which is essentially the price discovery. Can I predict prices in order to reduce risk, which I would face or any trader would face, right? Or any investor would face. Then the determination of the spread meaning depending on what price I buy at versus what price I end up. So your buy versus sell options, right? And the quotes, your intraday trading behavior. So that is what comes under statistical econophysics, where you're looking at stylized facts. You're trying to study whether an investor is looking at charts, whether the investor is basing his or her actions on fundamentals, or is just a noise trader. Is just a one-off person who decides that today I will switch on my computer and buy a few shares, right? So essentially, chartists, fundamentalists, and noise traders are the three categories. And then the behavior of these three with respect to price discovery, with respect. So when you want to look at how these three are interacting with each other, that's where you get agent-based modeling and how they interact with the markets. Right? In the first part, you are only looking at the actual assets, how they're developing, and so on. In the second part is where you look at the behavior of these investors. Right? That's what I mentioned when I mentioned agent-based modeling earlier. So that's stylized facts. However, the interesting fact is stylized facts were not introduced with respect to financial markets when they were first introduced. They were introduced with respect to growth phenomena for economies. Okay. So that's essentially a few papers, the most well-known papers with respect to high-frequency data, which actually study these stylized facts in terms of random walk behavior, in terms of martingale behavior of asset prices, and trying to see whether or not they actually follow a random walk, or in this particular case, whether they follow a martingale, right? And then with respect to volatility modeling, in time series, you have a whole section on volatility modeling with respect to heteroscedasticity, conditional heteroscedastic models, and so on and so forth. And the last one is that the last one in terms of the studies are that successive returns are not correlated. The last 3 points over there are essentially just all the studies in these three categories of random walk hypothesis, papers which have dealt with serially uncorrelated returns and found those using the variance ratio test of Low and McKinley. That's the most popularly used test to see whether or not returns are serially uncorrelated, and volatility modeling, right? Agent-based models essentially are with respect to, like I said, with respect to the agents. So you have a paper, the seminal paper by Stiegler in '64, which was the first to simulate trying to understand the behavior of these agents based on the regulations. The regulations. So SEC is essentially the US regulator for the financial markets, the Securities Commission, which actually, and he actually found that it lacked the rigorousness in terms of testing whether the regulations were effective or not in trying to discourage the investors from what you call doing anything in terms of how was it regulating the investors, right? So what they proposed was the rationale behind the study was that the demand and supply are essentially erratic, and your bids and asks, which the investors are actually putting up, are dependent on the random circumstances of the individual traders. So what they said was it is going to be very difficult to say that because of this regulation, all the traders will behave in a certain way. That's not going to happen. Okay. That's actually also, you can say, one of the seminal studies if you were looking at behavioral finance, right, where you're trying to understand the way that traders would react to certain information which comes in. Garmin in '76 is also an important study with respect to an analysis of market microstructure. And the last one was one of the first to actually, the three categories which I mentioned, they were one of the first to study those three categories of investors and traders in the markets. What have I not covered? I've not covered limit order book dynamics, wealth distributions, the macroeconomics of it, rational and adaptive expectations, and the related empirical aspects. Just in terms of very briefly, word of caution, when you're applying concepts from physics to economics, never do it blindly. Try and understand both the concepts in adequate depth before applying. Adequate depth because economic theories do exist. They do have empirical distributions. They do have studies which would say that the behavior of returns should be in a certain manner depending on the assumptions made, depending on the distributions at hand, and so on, right? For the financial part. If it were in any other field in terms of trade or any other sort of, like I said, the vanilla model of the gravity equation does not include transaction costs, for example. Study what it means for two economies to trade. What do they have to encounter, right? What do two economies have to encounter? At the same time in physics, go and study why it's important or how are you thinking of applying a concept to answer this economic problem at hand. right? So Galagati actually have a paper regarding the worrying trends in econophysics in 2006. So for those of you who may want to sort of look at the flip side of it, can feel free to pick up that paper. But as I've run out of time, I'm not going to give you all the examples that I've put here, but I'm happy to take questions at the end. And I'd like to end with this quote from Feynman in The Character of Physics, Physical Law, where he says that nature uses only the longest threads to weave her patterns, so each small piece of her fabric reveals the organization of the entire tapestry. Right? Thank you. Emma, back to you.
Thank you so much, ma'am. Now, Bijan will take the questions.
We have few questions and it's there in the chat box, but I'll ask the people who ask the questions to ask. So first was Kumar Adarsh. Kumar, do you want to ask the question? Okay, I'll just ask that question.
Yeah.
So his question was, can we relate going from microeconomics to macroeconomics as going from quantum mechanics to classical mechanics?
Yes, yes, yes. I did think about that. Very what you call wise analogy. Yes, you can think of it in those terms, but not completely. The reason being the following: you cannot think about it. You can think about it if you want to, as saying going from micro to macro. But why you cannot think about it is the following: microeconomics is not dealing only with probabilistic behavior of economic agents or economies, for that matter. Macroeconomics is not dealing only with the probabilistic foundations, because of which you cannot make that direct switch. So on those grounds, if you're saying, because quantum, what you call, when you're looking at quantum mechanics versus classical, you're going from that probabilistic to sort of you're moving from it, right? But in microeconomics, you're not starting with the probabilistic foundations to start with. You have already existing laws which exist for these individuals or for these economic representative agents. So on that ground, you cannot make that claim. But yes, in terms of the very simplistic view of micro versus macro is going from, say, atoms to light years, essentially. Yes, in that sense, yes, but not in the actual sense of the term, no.
Ma'am, added to that, so when we consider statistical mechanics and if you're considering a gas, for a single gas molecule, we cannot predict how it moves. But then when we consider the entire system, we can make a prediction. Does that work for economics as well?
Right. So in economics, in terms of finance, I can think of it as in make that analogy, because in finance, I can say that I cannot predict one individual trader's behavior. I will take a group of people as representatives to this particular market and then try and figure out their distribution, etc., with respect to the returns, with respect to the behavior, and so on and so forth. So, does that answer your question?
Yeah.
With respect to some of the traditional concepts of, say, a village versus an economy, it depends on the concept at hand. Like I said, with respect to finance, I can make the same claim. But with respect to, say, extending how a village would behave, sort of people in the village would behave versus how the economy reacts, would be very different.
So, we can consider the time ensemble for a large number of time and make a prediction, consider an expectation value and make a prediction there. Can we do that?
Prediction for? Sorry, I didn't get the last
So,
one.
if we consider a time ensemble of stock prices over time, can we get an expectation value? Because like you said, when the demand, so for a particular product having a higher price, the demand will be low. And it will be high for a lower price. But then because that demand is low, in time, I believe the price will come down and it might lead to an equilibrium, right?
So yes, so if it is away from, so if it is not at equilibrium, then yes, it will move towards equilibrium. So you're right, in terms of the market moving towards equilibrium, yes.
And the next question was from Deepak. Deepak, do you want to ask that question or should I take it on?
It's okay, I can read it in the chat. Microscopic systems are electrons in physics, but what can I think of micro systems in economics, right? So just like I said, depending on the question. So one thing which you always have to remember in research is be extremely clear about your question. It's because based on the question is dependent, it depends, the answer depends on that, or how you're going to then follow through to find the answer depends on that. So to answer your question, just like you can think of electrons in physics, you can think of individual agents in economics, right? So I can think of, if I'm looking at income distributions, I can look at the number of people in say Mumbai city, right, for example, or smaller, even smaller, say all the people in say IIT, for example, right? Income distribution in IIT is not going to be what you call representative of the income distribution across say Mumbai city. So you can think of it as the micro systems, yes, but you cannot make those extensions like the physical law extensions. That is what you have to remember.
Yes. Next question is from Lena. Lena, do you want to
What
ask that
can be
question?
a bridge course for a physics student interested in Econophysics? Well, you will definitely need strong foundations in not just physics, but in statistics, mathematics, and finance, all three. That would be my answer. But it's not a bridge course. You will have to take up adequate courses for these three. You can think of a master's in economics, which would then have electives in each of these. A master's in economics would have electives in these. But I'm pretty sure that there are universities across the world which would actually offer these interdisciplinary courses as well. Yeah.
Next is from Yash.
Yes, like statistical mechanics, even thermodynamics is in analogy to some. Yes, you're right. Given the Adam Smith, yes. So, what are the different ways one can use the laws of thermodynamics here? So, okay. So, I think this is coming from the fact that I introduced, I think, the principle of entropy also. Is that right? Yes, if you're still here.
Yes, ma'am.
Yeah. So, is that your question?
Yes, ma'am.
Yeah, okay. So to answer your question, to go back to where I was in terms of the principle of entropy maximization, what I would like to say is in economics, you have what is called utility maximization if you're talking about the consumer. And you have, if you're talking about the firm that's producing the goods and services, you're talking about profit maximization. A company always wants to maximize its profits, subject to the constraints that it would face in terms of the inputs, right? Inputs meaning, say, the labor involved, say, how much money does this company have, and so on, right? Those are the constraints. Similarly, in principle of maximum entropy, what are you trying to do? Your premise is that when you're estimating this probability distribution, you select the distribution which leaves you with the maximum entropy, right? Which is consistent with your constraints. So obviously your constraints have to be satisfied. So in that way, these two are analogous because you're talking about the laws of thermodynamics, say entropy maximization, but in economics, you're actually talking about one of these units, the economic concepts of either utility or profit. If you're looking at it from the flip side, for a firm, you could be talking about cost minimization, where you want to minimize the cost subject to certain constraints which the company may be facing. Does that answer your question?
Ma'am. Yes.
Okay, thank you.
Next, Chintan, you can ask the question.
Okay. Hello, ma'am. So, ma'am, my question is that, like in physics, we have certain laws which can be used only to a certain limitations. Like we have the Wayne's displacement law. Over a certain range of temperature, it falls. It doesn't work. So, what is the limitation of using? Like, can I have some example? Like, what is the limitations of using this data? Like limitations of the economic data that we use in economics. Yep.
Okay, so that's a good question. In terms of saying, by the way, all the questions have been really good, so thank you for that. Chintan, to answer your question, the limitations of economic data are on different levels. One is with respect to what is reported. Reported meaning you may have come across in the last few years the validity of data, at least in the Indian context, being questioned. GDP data, the gross domestic product data. You can read about it, but if you've not heard about it, there was this huge debate about whether the figures of GDP that India was releasing, whether they were authentic or not, right? So in that sense, what you have is nothing but that is in terms of reliability. Now, but to sort of support my opinion about that debate which existed, I believe that we still have a much more robust system in terms of data reporting compared to many other countries. So, in that regard, I think we are much better. Yes, there have been lapses in terms of data not being released at some points, which I don't approve of. But in terms of, so that's to answer the reliability part. Then comes the calculation part of it. Calculation in terms of what are the procedures used to sort of record these values. So if you do what you call do any study with respect to formulating a survey, some of these issues will come out. Reporting and recording of data. For example, if you walk into someone's house and ask them what their income is, because you say you want to do an economic study, people are not going to reveal their income to you, right? So then how do I figure out what is the income of this household? I still have the data with respect to, so I still have the economy projecting that the incomes are growing at such and such a rate, savings are growing. How are they getting this information? The way that they get their information is then looking for additional questions. Additional questions is how much do you spend on rice and wheat? How much are you spending on your television? How much are you spending on a computer? Durable and non-durable goods, essentially, right? So that is data recording. Is the data being recorded accurately? The person who's then reporting it, is that person being truthful about what they are spending, right? So that's reliability, reporting, calculation. Calculation is with respect to saying that, like I mentioned, what are the tools which are being used to assimilate this data? So is there, and then there's one more additional point, data entry. Were there any mistakes made at data entry? So in economics, there's a very famous international trade paper which actually resulted in many US policies being built based on the findings from that paper. And I'm not sure you would have heard of the authors Rogoff, etc. Some European PhD student, he asked for the data from the authors saying that I would like to replicate the results because I'm doing research in the same field. And he found that there was a very minor statistical error which ended up changing all the results. Okay. So in terms of data, data can tell you many things, it can teach you many things, but you have to be very careful when you're dealing with data. What is the data source? Is it a reliable data source? What inferences can you draw from the data? So these are some of the important facts that you have to keep in mind when you're dealing with empirical data. Does this answer your question?
Yes, ma'am. Thank you, ma'am.
You're welcome.
Ma'am, I have a question. Like, what is the difference between econometrics and econophysics? Like,
okay, good question. So in econometrics, you're dealing not just with. So yes, you have tools which can help you answer different questions, not just over time, even at a point in time, depending on the question that is asked, right? So you are actually taking statistical tools, statistical and mathematical tools predominantly to try and answer this particular what you call question. So for example, and then when you come to say econophysics, you look at concepts existing in both these fields and you try and see how one can be applied to answer the other, not analogously. You're trying to use these concepts to answer something else. Just like I showed you the gravity model, right? It's trying to answer, it's not telling you the force that exists between two countries, right? In economics. It's telling you how exports are driven by that particular equation. So you have to, it takes one additional step of thinking in terms of seeing how I can apply that concept of physics, concept of say the kinetic theory of gases, your Boyle's law, etc., to answer a question in economics. Whereas in econometrics, what am I doing? I have these number crunching. It's very commonly sort of said as number crunching models. They're not typically just that. Trust me, they are much more well thought out, and they have their own advantages and disadvantages of using one model over the other. And your question determines which model you will go with. So it's basically data analysis, techniques of data analysis, which are not drawn from any specific sort of area other than statistics and maths put together. That would be my understanding of it.
Thank you, ma'am. I guess that, like, does anyone have any other questions for ma'am?
Is Godni ma'am also there? Because I didn't see her name at the start, otherwise I would have wished her.
Yes,
I'm here.
she's
I
waiting.
Hello, ma'am.
I joined little late, maybe around
No problem.
past
Good
10
evening,
or
ma'am.
yeah. And if Jitin has the questions got over,
Yeah, I guess the questions are over.
Ma'am, you can, you may.
yes, I would like to first say to Aditi that I'm 100% sure that you are a very, very good teacher. Students appreciate you as a teacher. I still remember you having you had come to me when you were going to TY, and you had said that you are feeling very sorry that you are leaving physics and going for maths. But I think that has proved very fruitful for you, because now you have gathered a lot of knowledge, accurate knowledge of not only physics but also maths, stats, and economics. And really, that is a very good combination, and that must have helped you lot when now you have developed yourself in this particular field. And I think it was a very good decision of yours of going for maths, even though you were interested in physics, because then you kept studying physics on your own. That is what I can see from what you are, the way you are explaining things today. So I'm very happy to have you here and having heard you here today.
Thank you so much, ma'am. That means such a lot coming from you. So I still remember so Bodhini ma'am was one that I went to when she was teaching us a paper, and I asked her the same question 3 times at 3 different points in time, because for some reason I would just not understand it, and the third time is when I understood it. But she would very patiently listen to all my doubts, all of them. So Bhuti ma'am, Veda ma'am, Mistry sir, they were all very kind, and I've learned so much from them. Any physics that I remotely remember is all because of what you've taught. So that goes without saying.
But having heard to you today, I find that the way your lecture is being delivered, that skill that you have got is also excellent.
Thank you so much, ma'am.
Welcome, and I'll be very happy to keep calling you as and when I want my students to listen to this particular branch, listen about this particular branch.
Sure, ma'am.
Okay, back to Emma.
Thank you, ma'am. So now we'll have Adya to give the vote of thanks. Adya?
Thank you, Emma. Good evening, everyone. I'm Adya Navalkar, the operations at this year. On behalf of the entire Society of Physics, I take this opportunity to extend my thanks to Aditi ma'am for taking time out for us on a Sunday evening in between your IIT exams and educating us on such an interesting topic. A lot of us were looking forward to this lecture, and we were glued from the similarities between physics and economics, the tangent gravity model and elasticity till the very end when you were talking about the precautions. This fun going beyond physics to economics, stats, and finance. As a student of physics and stats, this was particularly interesting for me. Pretty sure other stats students felt the same. One thing that piqued my interest was statistical econophysics. I can't wait to study more about it. Thank you again, ma'am, for coming. You're also very.
Yes, sorry.
We're saying we are very grateful to the entire Society of Physics team and all the volunteers who made this event possible. Also, a hearty thanks to all the professors for their support and cooperation. Lastly, I would like to thank the audience for spending the evening with us. It was indeed lovely to have you all. We also have more events lined up, so do stay tuned. Thank you.
Thank you, Adya. Thank you so much. Is Jyoti
Okay,
ma'am
yeah.
still there?
Yeah, I just wanted to say, Aditi, a fantastic lecture delivered with great study. The depth of knowledge of your subject really
Thank you so
showed
much.
through. And as Bodne ma'am was telling you, I also remember all those days came back to me when you were a physics student and all that. So very happy to see you grown so much in your subject and your studies. Very happy to have you. And as Hamla madam said, we'll keep calling you back for this particular
No
branch,
problem.
which is really something that none of us in the department really have looked at. So it was a very good opportunity for us also to look at it in so much detail. Yeah.
Thank you so much,
Thank
ma'am.
you.
My
Yeah.
pleasure.
Bye.
Yeah, so unlike our normal offline sessions, here we'll only have to leave the room. Thank you so much, everyone, once again. Thank you so much, Aditi ma'am, Jyoti
Thank
ma'am,
you.
Bodhe ma'am, and everyone here. So I'd request you all to start leaving the room.
Thank you so much, Emma.
Thank you,
Aditi.
Eva, and all the students of your Society of Physics for making such a good planning of all the events that you are doing up till now.
I
Thank
guess
you,
there is
ma'am.
a last question if ma'am is interested in
Yes,
answering.
yes, anytime.
Okay, okay.
It's in the chat box.
So,
Yash,
okay.
do you want to ask it directly?
Is there also social physics? Yes, there is social physics. What are the fields of interdisciplinary physics related to arts? So social physics, I would urge you to go and read the paper by Majorana, which actually talks about the wealth distributions. But other than that, you can actually see there's no end to where you can apply physics. Very frankly speaking, from what little I know, I can tell you that the reason being physics is everywhere in terms of trying to explain all the phenomena around us. So in that sense, it is just you and your imagination as to what you can do with applying it. Now, this is me being asking you to be creative, but with respect to existing fields, yes, social physics does exist, and just like econophysics. In fact, like I said, I keep going back to the same example, but yeah, maybe I should have thought of other examples in terms of, say, the gravity equation or elasticity or utility. So optimization, right? Optimization problems are a big deal in terms of economics. You open any standard economics textbook, you will have optimization with respect to a consumer, with respect to a firm, and so on and so forth, with respect to an economy. So just like you would have, say, entropy maximization. So think about these parallels. But in order to be able to think about the parallels, know one subject fully thoroughly, in your case physics, before trying to look at other fields. Because what tends to happen is if you start jumping, it's like trying to get everything at the same time. So that is actually, then you're essentially at a sort of you need to have in-depth understanding. Like I said, with the word of caution, you need to have in-depth understanding of both the disciplines before you can actually venture and say that, okay, I think I could apply this to try and answer this particular question in this field. And that does not restrict you to saying that you cannot apply an economics concept to physics. You could look at the other way around as well, right? Think about it. If you have any doubts, you can get in touch with Vision, you can contact me, and we can take it from there. Does that answer your question, Yash?
Yes, ma'am. Thank you.
You're welcome.
Thank you so much, ma'am. And also, ma'am, can you share the PPT with us if you can?
Sure.
Yeah.
Right? Thank you so much.
Yeah. Thank you so much, ma'am.
Yeah.
Thank you
Thank
so
you,
much,
Aditi.
everyone.
I will be very happy to meet you in